So welcome back. Let's start module 6.2.3. And we also do the module 6.2.4 and module 6.2.5. This is a continuation of the previous module on using focal point plasticity or cell links in CompuCell. What we have done last time was modeling using cell links at the XML level and see how it works. What we're going to do in this module is, in the next ones, is to see how we can manipulate the cell links at the Python level to model other processes like cell crawling and conversion extension. So before I continue, if there are any questions from the previous module, I'll be happy to answer them now. So here we're going to still be using links between cells, as you see here on the left, but we're going to be use that actually to model, manipulate those links at the Python level to simulate things like cell crawling, as you see here on this snapshot on the right. So what we have done so far is just use the manipulate the links at XML, right? Which is nice, but once you set the links, right, set the parameters, you can only run them as they are, right? There is no dynamic notification of the links. You cannot make a cell to have more links or less links or stronger links or weaker links, giving any change in the emitted environment or some external input that comes in the model, right? All your cells are doing different things, but have the same set parameters. Manipulate the links at the Python level allows you to change these links every now and then according to some kind of input or some other given frequency. So to have full control of when and where the links are created, you have to go to the Python level, which also allows you for links between cells at the same time to have different properties. Maybe we have type A and type A cell interaction on your right, and you also have type A interaction to the left of the cell, but for some reason, the links of the cell on this left should be stronger than the links of the cell on the right, even though it's links of the same cell type. So this is something that you can only do at the Python level, which you're going to learn now. So the first thing we have to understand and do enable to allow the link manipulation at the Python level is to tell the plugin on the XML level to allow for these local interactions or the local modifications. So this is done by going the plugin Focal Point Plasticity on an XML. And you may have noticed that there is a local tag there that was commented. And this local tag is actually the flag that tells the CompuCell player or your program to allow these modifications at the Python level. So the first thing that you want to do is to uncomment that if you want to have your modifications at the Python level. One thing that you have to notice is that turning on this local tag flag in a Focal Point Plasticity does not turn off the links from the XML level. Everything that you set up on the XML are still valid, so if you set your cells of type A and B to have up to 2 links, right? Whenever a cell A, C, 1 cell B or more, it can make these links with the other cells in an automatic manner because that's what you set up on your XML level. So whatever you set up on XML, that's going to still work. The cells are going to still make links. They're going to still break at the same maximum distance. They still have the same number of links per cell pair. They're going to have the same string. Everything there is going to still work just as you set up on XML. So, but if you are manipulating your links at the Python level, maybe you do not want those all link activity that you set up on the XML to still happen, right? So if you don't want the player to do any of the links automatic links manipulation or creations and destruction that you normally have on the XML level, is better to turn off all those link parameters on the XML. And the simplest way to do that is just set the maximum number of junctions to be 0 of all the link pairs. When you set the maximum number of junctions to 0, that means that doesn't matter which parameters you set up for that specific cell pair, they are never going to be created. And if they're created, they have to be created from the Python level. So that's something that you probably have to, if you use the local or the Python level manipulation of the links, you probably also want to set the maximum number of junctions to be 0 for each interaction pair. In this case, the links can only be manipulated at the Python level. Okay. So in some cases, you won't have a background of links and set up specific links, special links, given certain conditions. So you can have this XML control of the links. And on top of that, you add your Python level layer. But most of the time, if you use the Python level layer links, you want to set up all the maximum junctions to 0 to completely turn off. But the parameters, they still have to be there. They still have to be there for you to be able to modify on the Python level. As far as I'm aware, they still have to be declared. All the possible parameters, they still have to be declared there. Okay. So once you go now to the Python level and you are just Steppable, how can you manipulate the links? Okay. So you can get all the comments from the tweeted. You just go to CompuCell3D Python, go to Focal Point Plasticity, okay? And here you see a lot of options of everything that you can do with the links. So you have link inventory, got the anchor, link, number of anchors, number of internal links, number of external links, number of link junctions per type, number of links. You can create a link within the cluster, outside the cluster. So when we use compartments, we are not caring for the compartments. You can delete all the links of a cell of any type, or you can delete the specific links. You can get information about any link property, okay? And you can also do loops to visit all the different types of link that your cell can have, on the internal or on the external. Our anchors or cells touched by link. So you have all these options that you can play with from the Python level, and it's too much options for me to go over all of them. You're going to just be using a few of them. So of the few of them that you will be using, I'll say that these may be the most important ones, okay? So you definitely want to create a link, okay? So probably be using this one, link management, create FTP link, and that pastes this command that you see here, link equals self.new FTP link. And then you have the first two entries are going to be the two cells that's going to create, that's going to link together. The first one is the initiator, and that second one is the initiated. So a link extends from this cell into this cell. In some cases, that may be important. In all the examples that you're going to do here, it doesn't matter. You may add cell 1, cell 2, or cell 2 and cell 1, and it does not matter the sequence. So basically, you'll be putting the first two entries are going to be the two cells that you're going to be linking, okay? The next entry is going to be the lambda distance, okay? The lambda, the force of the link. The second is going to be the target distance of the link. And the last one is going to be how far the links can be stretched before it breaks. So the same thing as we had before, but now you're seeing that on the Python level. You can specify who you are linking, the strength of the linking, the ideal length, and the length at which it breaks. Basically, that's it. So it corresponds to these terms here. The other thing that you'll be using is going to be deleted links to attach to the cell. So you're probably gonna go loop over cell, select a cell, and from that cell you can use the command self.remove all cell FPP links, and then you just specify from which cell we are removing the links. So these two will be using all the time in this exercise, okay? So we see that there are a lot of options, but you only be using two of them, okay? Now, this is the basic of what you can do. Create link, delete links, right? Now, the question is, okay, what can you do with this? So one biological process that you can use it is to model cell crawling, okay? So I do not know how many times you have seen a cell crawling model in this workshop, but I'm giving another one and later even another one, okay? So that just reflects the fact that uh, giving one cell processes, there's many ways you can model it, and there's certainly true for CompuCell. If you say, I have a CompuCell3D model of cell crawling, there are many ways you can do that in CompuCell, okay? So just to revisit, cell crawling, the process by the cell starts moving along a substrate, can be ECM, can be other cells, and the cell extends a protrusion, grabs there, and keeps extending protrusion and pulling itself, so it moves itself forward. So there are many ways that you can achieve cell crawling on the substrates by polymerization of actin in the limipodia and contraction of the actin on the back, which pulls the cell forward. Then you have the addition points of the cell on the substrate and push itself forward. And on the bottom here, you just see a movie of a group of cells moving along a tissue. And that's a case of cells, in this case, a bunch of cells moving along a substrate, okay? And when you talk about cell crawling, we usually mean that, right? So there's a few examples of cell crawling on a substrate, okay, which the lateral line or the zebrafish angle is a clear one case where this happens, okay? But in most times where the cell is crawling, it's not crawling on a substrate, but it's crawling in a three-dimensional environment. So you do not really have a ECM substrate, a carpet for you to move on, okay? Usually when the cells crawl inside tissue, especially immune cells, right, that have to go into the tissue, uh, they actually crawl by there's not a clear ECM for them to attach to. They crawl by just moving and using the neighboring cells as anchors. So here's a movie, I don't have the reference here, sorry, of neutrophils and macrophages moving inside the tissue. So in deep tissues where you have the cells go inside, you are not seeing the other cells, you're only seeing the neutrophils in GFP and macrophages in RFP, I believe, in the two different fluorophore colors. Okay, and then what you're seeing here is that these cells move by extending a lot of protrusions, right? And pulling the other cells around and use the other cells in the surrounding tissue as an anchor, right? So this is a process that you can model very easily using the links that tool that we just learned in the previous module. Because what can you do? You can select a cell and make the cell to start to link to the cells that is in front of it. So you have to define where the front of the cell is and what the back of the cell is. So this assumes a previous polarization of the cell. And then the cell, link the cell on front of it at a distance that's further from its target distance, and then it pulls. And then every now and then we model the link so the cell keeps pulling forward. Okay. So that's going to be a good way to model this crawling in deep tissues. Okay. So that's more or less what we want to do now. So this is going to be a basic model. We assume that the cell is polarized this way, and it has the ability to creating links to the cells in front and gonna push the cells towards each other because we're probably gonna make a target distance to be very close to 1 or 2 pixels. So the cell pulls itself, propels itself forward, and by doing these links all the time, the cell can push itself forward as you see in this movie. So here you see the yellow cell and 3 of links at every time, and then by creating these links always in the same given direction, it can propel itself towards the right. Okay. So, and what is the nature of these lines here? That's basically the links that have been used before, but we control them from the Python level, so we can have constant creation and deletion of those. So you delete the old links, create new ones, put the cells put itself, delete the links, create new ones, put itself forward, delete the links, create new ones, put itself forward, and then so that's what we want to code. So we're gonna code this together, and by now I think you should already be very good at coding the create simulation from scratch. So let's now move on to our next exercise, our first exercise of this second session. So let's go to tweet it and create a new model, right? So we go to menu, CompuCell3D project, a new CompuCell3D project. Give it a name, maybe cell crawling tissue, select Python XML, hit continue. And this time, let's select the dimension to be x equals 84 and y equals 35. And this is important, make the both directions periodic, okay? So you want to be to x to wrap itself around and also the y to wrap itself around, okay? Just because then the cell can keep going, you can run simulation a lot in a loop, right? But if you don't do periodic, that's okay. It's just at the end the cell can only do one run, and that's going to be the end of your simulation. Okay. Then you create 2 cell types, a cell type named red and a cell type named crawler. Okay, that's going to be the yellow cell. Hit add to compare to the table, hit continue, ignore the chemical field. On the next window about all the cell properties, you select contact, volume flex, and focal point plasticity, and some neighbors, and hit continue. And once the configuration is done, you hit done. Okay, so your first task is to do that on Tweetit. If you don't want to do this, you want to go get the code for you, you can download the file 6.2.3a zip and open the code. So it's up to you wherever you want to practice making a new model or just download the file. Either way, please let me know in the chat once you are done. And also let me know in the chat if you have any questions about the setup process. Yes, use periodic boundary conditions. I mean, just that then if you use periodic conditions, then just I can be going around and around me, do multiple runs. Yes, no, see, it's something like that. That's what you should get by just doing this. Now what I'm going to do next is going to change the conditions to make it something that looks more like the video there. But that's exactly what you're going to have after you run this. So the next slide looks exactly like this one. Maybe what you want to do now is make your red cells red and your crawler cell yellow. Okay, Joanna got it. Nelson got it. Okay, so let's continue. So what you should get is some initial conditions that look like this. You create subset of cells. There are links between them. So you have to, the wizard can only go so far. You always need to then fine-tune simulation to get exactly what you want, right? So the first thing, let's go to the XML and initializer, and let's make all the cells red, of type red. So there you have red and crawler. Remove the crawler and make them now red. Okay. We already know that we want to manipulate the links, use the focal point plasticity on the Python level. So let's uncomment the local tag. And we don't necessarily want the red cells to have links between the cells. We want them to be a little bit more loose. So any the one Well, you only want the links between the crawling cell and the red cells, right? So what you want to do now is set all the maximum number of junctions to be 0. So no links are going to be created unless you tell the program to do so. Okay. So, and lastly, on the contact plugin, set energies to 2.0. Okay. 2.0 is usually a low level of energy, but I want to make our cells more mesenchymal, right? So more have a rough boundary. So set the contact energy is low, so they're going to be more fluid-like. So if you do this, okay, the structures are still there. You should get some that more or less look what I have on my screen, right? If you don't want to do that, you can just go ahead and download the code 6.2.3b, and you're going to get exactly this point, right? So let me know if you're done, and before I can proceed to the next slide. Did everybody got something that looks like this? How to change the uniform initializer so the cells fill up all the space. Go to the uniform initializer and make the X and Y to go from 0 up to the dimensions on the X direction, which is 84, and the maximum dimension on the Y direction is going to be 35. Yes, you can comment, you can even delete everything that concerns the medium on the FPP links. And the contact is bad to leave it there. CompuCell might complain that there is no specific contact energies between the cells and the medium. So even though you're not using on that part of the contact, it's better to leave it there. Okay. But the FPP links between the cells and the medium, then those you can delete. So do everybody get a full the space fully with red cells? Or you may, okay, Clara, my simulation is running, but I don't see anything. You may have made a mistake in the uniform initializer and you end up with no cells. Did you get cells, Clara? Okay, excellent. So now we have a field of view that a space filled with red cells. We set the contact energy to be low, so they look very mesenchymal-like, okay? And what is missing? You are missing the crawler, right? The cell is going to crawl. So we have, let's put the cell crawler there. So you can do that by maybe, there are two ways to do this. You can add a new region in your initializer and add the crawl cell a specific space, okay? Or you can do that on a Python level. I like to do from the Python level, okay? So let's go to the Steppable files, and then in the start function, let's find the cell that's on the left and in the middle, in the center of the simulation, and let's set that cell type to crawler, okay? So you have to, one thing you can do, you can loop over all the cells, check if the X and Y directions are within a given range. All right, given the range between 7 and 21, because each cell is about 7 pixels. So pick up the cell that's between 7 and 21, pick up the cell that's within this range here, right? And then check if in the Y direction it's in on the 14 and 20 light sites. And once you find a cell, set to type crawler, and then you break the loop because you don't need to check for the other cells. And also you only do one cell crawler, not many. So try to code this in the simulation and see if you can get a cell crawling, a single crawler cell on the left, just like your colleague did here. Anastasia got it, yes. So try to get this output like I have on my screen, and as Anastasia has. All right, so I see that you guys got it. Harini got to the other side. It's fine, but on the next slide, everything that I said that's going to be plus X direction, you have to do minus X direction, okay? But it's fine this way. So if you're still coding, I can show you an example of how to do this. You can go on the start function, loop over all the cells, okay? And then just check if the cell center mass between 7 and 21 and the cell center mass on the Y between 14 and 28. Make it a cell crawler and break. Okay. Right. So if you want to code this, you can just download the file 6.2.3.c.zip and you get the code. You're gonna get this code already coded, right? All right. So now becomes the heavier part of the coding to add the cell to create links to the right and move to the right. Okay. So first thing that you want to do, let's implement the model. So this was just initial condition. It's not the model yet. Okay. It's not the cell crawling model. The cell crawling behavior is not model yet. I'm going to do this now. So the first thing you want to do is set some kind of global variables, okay? So we know that you're going to have a maximum angle, right? Well, it's going to have the lambda, the strength of the links, the target distance, the maximum distance, and you also want to extend links within this kind of angle range to the right, but maybe between, let's say, 45 plus or minus 45 degrees, or plus or minus 30 degrees, or plus or minus 6 degrees. You can choose the range. Okay. Yeah, it's going to be the angle of the link because your cells not necessarily going to be right in front of you, right? They may be a little bit up, a little bit down. So you have to allow some kind of angle range for you to link the cell. If you only allow the links to create if the cell is right in front of you along the x direction, that will never happen, right? So you have to allow some kind of angle allowance for the cells to bring. And also we want to do maybe 3 links at the same time, like I did in my movie. So you want to grab more than one cell in front of you. Yeah, the proposal is to define the front of the cell. Okay. So you want to set all these 4 global variables. And when I use global variables, I like to make them capital letters so I know that they're a global variable. And then you're gonna set these numbers here: maximum angle to be 50 degrees, lambda to be 2, target distance to be 0, you're gonna pull all the way in, and the maximum distance to be 1,000. In other words, it never breaks. Okay, so do this while I receive one slide for your colleague. So let's code this first. So what he did, set up the global variables. Okay. Don't worry about this line here. This is just my cursor when I took the snapshot. Okay. Um, and let's start with these parameters here. You can then change them later and see what effect it has on your simulation. So question, what is math import star? Do you have to add it? Yes. Okay. So this math import asterisk or star imports all the math functions inside Python. Okay. Python has some kind of mathematical manipulations by default, but they are very limited. Here we want to do this math import, very important, because you want to use a tangent function. Okay, when you're going to grab a position of we have the position of the crawling cell, we're going to explore all its neighbors and grab the position of all its neighbors, right? And then from these 2 positions, you're going to draw a line and get how much angle it has from the horizontal axis. So that's a function called a tangent that it exists in the math library in Python. So you have to import that library first before you can use it. So yes, please do also add this line on for from math import star, because otherwise you cannot use that function later. You can leave the import in Python as NP, that's no issue. Is a problem if you do not do the Python version of the crawler for the rest of this lecture. It's not a problem as long as you follow along what you're doing, okay? You can always download the files and the solutions. But all the rest of this second part of the module is going to be doing things on the Python level, okay? You don't need to do them. You can just follow the class, and because the next exercise is going to be a different version of the same model, okay? But you can just sit and watch what you're doing and make sure you follow. You don't need to code everything. Remember, you have the slides upload to you, so you can always go back and grab them. And at the end of the session, well, we have those files. So in the end, you don't need to code, right? The file is there for you at different steps. Okay. So now that just setting up the global variables, okay. Now let's run the model, okay? And now let's make the addition and deletion of the links. So this has to be done in a cycle manner, okay? At every n number of steps, we have to delete all the links that we had before and create new ones, okay? So that's basically what we're doing. So in the step function, you have to add those following lines. First, we add some kind of statement. We have some kind of resting time for your system to relax the cell boundaries and for the crawling cell to be there, kind of moving a little bit, okay? And after this resting time has passed, so remember MCS is a timestamp of your simulation as tracked in the Python level. So after this is satisfied, every 50 Monte Carlo steps, you're gonna delete all the resisting links and create new ones, okay? So this MSS is the time of simulation, and this division, well, with this percentile comment here is the rest of the division. So you take your, for example, 5,000 times divided by 50, right? 5,000 is divisible by 50. It's going to give 1,000, right? The result, and there's going to be no rest to it, okay? If so, yeah, so this comment here gives the rest of the division. Okay, so when this becomes 5,001, there's going to be a rest one. If it's going to be 5,002, going to be a rest two. So this condition is not going to be satisfied. It's not going to be zero. It's only when you have 5,000 or 5,050, 5,100, 5,150 that this condition is satisfied. So that sets the frequency at which you do here. You call these functions. So Anastasia has a very important question. Delete links and create links function already exists in CompuCell? No. These are functions that you are going to create in the Steppable. Okay? So when you get a Steppable, you get you have 5 type of functions that's automatically created. You have the init function right at the beginning, right? That's just initialization of the Steppable or the class. You have the start function. You have the step function. You have the on-stop function, and you have the finish function. Do you recognize all those 5? Okay, I hope so. So they are always there, and then there's a little bit of explanation on the top, right? Saying when each one of them is used. The step is at the very beginning. Sorry, they start at the very beginning. The step is every Monte Carlo step. The finish when the simulation is done. And on stop, I believe on stop's the name, is when you hit stop in the player, then it does all the commands that's under there. Okay. But your Steppable can also have other functions that you define. So that's what you're going to do. You're going to define a function that go over all the cells, and for all the cells, delete all the links. And you're going to define another function called create links that go over all the crawling cells and make new links for those crawling cells, okay? So the first one is to remove the links, the other one's to create links, okay? So why I did like this and not just write all the code inside here? Two reasons. First, your code's gonna look cleaner if you break it down in functions. And second, it's just good programming practice to break your things into functions, okay? So let's do like this. So right now, just add those 3 lines. And once you're done, we're gonna go now code the self-delete links function and the self-create links function. Let's move on down to the next slide. Okay, so let's first define this self-delete links function. So to do this, you get outside the step function and start to write def delete underscore links, open and close self column, okay? And this def here has to be in the same indentation as this one, okay? So it becomes its own function. And inside this def delete function, you have to then have a ident inside, and then let's do a loop over all the cells of type crawler, okay? So do a cell loop over all cells type crawler. You can use the CompuCell3D, CompuCell Python ML, select visit all cells of a given type, and then select cell crawler. And inside this, for all the cell crawlers, so this can work with more than 2 crawlers, okay? You use the and now an intrinsic function called self.remove all cell FP links of that cell. And then that's going to be your delete links function. Notice that when you define the function, definition of the function delete links, you have to specify self as one argument because you want all the comments inside this function to inherit all the comments that start with self dot, okay? And when you reference this function, when you call it from other functions, from the step function or from the start function, you always refers to them with the self dot in front of the name of the function, okay? And you can also pass arguments, but we're not going into that right now. Are you allowed to define functions after you first reference them? Yes, you are, as long as you define them. Yeah, so this can be done either before or after. So in this case, you can see from my enumeration that is after. Yes, exactly as Joanna has pasted in the chat. Is it because you have defined create links function yet? No, then we're going to give you a different error. Okay. Check if all your spaces are spaces and not tabs. That may be the issue. Yes, saying the line is going to help a lot in the debugging. I think the issue is resolved with Joanna. Okay, so this is going to be a very simple function. Okay, it basically go over the crawling cells and delete all the links that it has. Okay, is there a problem if you have no links yet and it's tell you to delete? There's no problem. I mean, if it doesn't have any links to delete, you're just going to ignore and move on. Okay. So now let's define the create links, and that's where that's a little bit more complicated, right? But not that much. So the create links, you're gonna also define a new function. And so gonna be def create link self. We're gonna go over all the cells of type crawler. And on top of that, we're gonna also go over all the neighbors of that cell. So you're gonna take the cell crawler and go over its neighbors, okay? And now for all the neighbors, you're gonna return the distance vector between your crawling cell and your neighbor. So this comment here, self.invariant distance vector between cells, cell and neighbor, is gonna give you the X displacement, the Y displacement, the Z displacement between the or the vector components of the distance vector between your cell and your neighbor. Okay. So this X, Y, and Z is going to be the vector components of the distance between the cell and the neighbor. Okay. So this is a comment that you can actually grab from the menu. You go to CompuCell3D Python, go to distance between cells, something like this. And there's going to be one of the options going to be vector distance between cells or invariant vector distance between cells. What's the difference between invariant and the version who has no invariant? Is that the invariant takes care of when the cells are on the close to the boundary using periodic boundary conditions. That's it makes a correction there. So because you're using periodic boundary conditions, you want to use the invariant version. So with this vector, right? So you know how much is in front of you, how much is above of you or below you. You can now, from this information, get the angle that this other cell has in front of it with respect to the x coordinate direction. So you just use the ATEM2, and then you give the y position and the x position in this order, okay? Y and x. And that command that's available from the math library in Python returns a number between minus pi and pi, okay? It's basically take the tangent between the two, okay? Now from that, because it returns an angle that is between pi and minus pi and pi, you probably want to convert that into degrees, which is easier to deal with. So this command here, degrees, and add the angle as an argument, is going to convert your angle from radians to degrees, right? After you convert your angle from radians to degrees, you can, it can be minus or plus, right, along the x direction. So you just take the ABS absolute, so you make that positive number, and then you check if this angle is going to be higher or lower than the maximum angle. So it's lower than the maximum angle, so it's inside that cone of 50 degrees, plus or minus 50 degrees that you define, okay? And if it's within that angle, then you use the comment to create a link between those two cells. Then you create a link between the cell, the neighbor, use the lambda, the target distance, and the maximum distance that you define up there as a global variable. So try to code this and let me know if Python does throw you any error, and let me know if you have any questions. So code this one now, this thing first. If you want to code this, if you just want to grab the code ready, you can just go to the sim material files and grab the code 6.2.3, and you should have it ready. Okay. But once you run simulation, it should look like this. Okay. Anastasia, you don't get any errors, but also don't get any links. So check if you untag the local tag in the XML file. Ah, you got it. Okay, good. Ah, yeah, you have to wait 5,000 steps for you to get the links. You can decrease that lag time to 1,000 if you are more impatient, if that's too long for you. And then you start get the link. So the cell gonna walk there, stay there a little bit, and after 5,000 steps, gonna start moving. Any shortcut to add this? Which part? This one here? Unfortunately, this one here, you have to do all this. There's not much I can do about neighbor and neighbor. Okay, the invariant distance vector is going to be the distance between the vector components of the distance between this cell and the other cell, right? So we're going to return this, because this is going to just return the x and the y. So if here's one cell, here's the other cell, you have this vector between them that connects them, and this comment returns your X and Y, and also returns the Z, but this is going to be 0 because everything is on the same Z plane. Okay. And if you specify this as A equal that, then this A is going to be a vector. But in this case, I specify X, Y, Z, so your comes break down into X, Y, and Z components. So for the the step function is right here on the top. Yes, it's invariant account for the periodicity. Otherwise, a cell is here, the neighbor is on the other side, and it's going to give this distance instead of the shortest one. So Clara, it seems that it's working, but you want to set the maximum number of chunks to be 0 for all the cell pair interactions. Because right now your red cells are also making links. I mean, you're not gonna. It should be okay. The cell should be able to crawl. Anastasia is getting links all over and no direction movements. Well, you're getting the links, right? So you're creating them. Check if your maximum angle is not 90 degrees. And if you're taking the absolute value of the angle here. Oh yeah, if you don't use the break, you can get multiple crawlers. This model should still work with multiple crawlers. So that should be fine. You can set your max, so that's something that you can play with. You can set your maximum to 90, to 10, to 50. So in my simulation, I have it to 50. So you can grab more than one cell at a time. If you make our angle narrower, you can only grab one at most, sometimes nothing. If you make it wide, you can grab more cells. Yes, the order of the variables in the arc tangent is very important. It has to be y and then x. Okay, so it has to be, otherwise we get a wrong result. Okay, Hipla got it. Clara got it, answer. So Kaya, if your crash after 5,000 steps, that's exactly when you start making the links. So maybe there's something wrong in either this or the previous one. So go back and check if it's working. Check if you have the links are specified but with 0, and if the local tag is specified. If you don't have the local tag on, that might cause a crash when you try to manipulate the links. So on Anastasia, you're making links all over, but you're making the link, so that's a good sign. Yeah, but because if you pull from all the sides, you never get anywhere, right? So check what your maximum angle is. If you set it to 90, you're gonna get everywhere. 50, okay, good. Did you make the change the tangent to be y and x instead of x and y? And I think you did that change, fix, but make sure that you save and run simulation again. Okay. Do you have this absolute value here? I think you do. Okay, Kaya. To get the a tangent function, you have to import the math library. So in our case, that's easy to fix. You just have to go back here at the very beginning of the steppables. Okay, where is it? Here, you have to add the line from math import star. After you do this, import the math library, then you have access to a10.2 function. Okay. So add that and see if you get it work. That comments cell invariant vector between cells, you should give two entries. one is the cell, comma, and the other is the neighbor. So it's not cell.neighbor, it's cell, comma, neighbor. Because it's the distance between the cell and and towards its neighbor. Rocio. Okay, I think that may be an issue that what the target distance you'll be using. Or maybe the lambda is too small. So use maybe you can try to increase that from 2 to 5 and make the target distance to be 0 or 1. So it pulls all the way back. If your target distance is 7, then the cell create the links, but it's perfect. Happy, keep the link as is. There's no force pulling. So you want to make the target, in this case, the target distance to be small, so the cell links and pulls itself. So Kai is working, Joanne is working, Russell, it's working for you. It still create the links, but not pulling. Okay. Did you check those values here? Okay. Question if the crowd should be moving fast. Well, that depends on what you consider fast or not. It actually moves pretty fast, at least in my computer. But you can change that if you make the lambda smaller to be 0.5, for example, then it's gonna the spoon is gonna be weaker, right? And then it's gonna move slower. If you make the lambda stronger, maybe move faster. If you change the angle, that may have an effect. If you make the angle very narrow, you can only click at most one cell in front of it. So that's not going to work very well. If you make the angle 90 degrees, then you're going to grab everything that's in front of it. Okay. Then that also may lead to some kind of issues. Maybe, probably if you make the maximum angle equals 90, the cell's not going to move very efficiently because it's pulling too many people. Okay. So you can try that. I have an issue with deleting links. Okay, yeah, that may also be the issue. Okay. You have to recycle your links, otherwise it cannot move forward, right? You have to let go of your past neighbors. Exactly. Rose, so that may be another issue that you might be getting. Maybe you set your step to be 5,000. Okay. Okay. You got it. Okay. Excellent. Okay. So it seems that now everybody got a working version of the model. Is that correct? If anyone needs help, please let us know and someone's gonna help you in the chat. For the ones that got it earlier, hoping that you had the time to see what happens if you make a stronger, higher lambda, weaker lambda, if you make the angle higher or smaller. And something that you can also do, you can go back and add 2 crawling cells or 3 crawling cells and see what happens. That would be fun to have 2 of them move at the same time. Okay. So let me just answer one question in the chat and then you can move to the next exercise. Okay. So you should be getting something that looks like this. And again, if you was too much thing for you to code, you can always grab the file 6.2.3D and then you should have this working version for you. Okay. So question for Anastasia. Before I use self.delete FP link, parentheses link, instead of self-remove all self-FP links cell, okay? Can you explain why that didn't work? Well, the first one assumes that you already have the link object that you have grabbed. So that presumes a loop over all the links of the cell, and then you delete one link at a time, okay? The second one, you just grab the cell and move all the links that the cell has. So that's the difference. So the first one, you remove the link, but you didn't specify what the link is, right? Or maybe there was a very early definition of what the link was, and then you keep trying to move the same link that you removed before. So that one leads one link at a time, but you have to make a loop of the links first to grab the link. On the second one, you grab the cell and delete all the links of the cell. That's what. Okay. So is everybody happy here? I know that there are a lot of debugging on this part because it actually involves more coding, but I hope that you are happy with the result. Okay. Now I think we only have time to do one more simulation. So let's do the same cell crawling method using links, but instead of have the cells using other cells to move, let's have the cell use the substrate to move. Okay. So the idea is going to be exactly the same. So we're now moving on to module. Okay, let me start this again. So let's now move to module 6.2.4. We're going to implement a version of the cell crawling on a substrate using anchors. So before we had a model of the cell moving among other cells and using the links, cell links to push itself forward. Now we're going to do a similar model but using anchors where the cell does not create a link with another existing cell, but the cell creates a link with a specific point in the space, okay? And that can be modeling like the that can be viewed as a Filippodia extension of the cell, that cell extends some kind of protrusion in front of it, grabs the substrate and creates an additional point in here, and then it pulls itself forwards towards that point, and then do another one. So the code for this one is going to be very similar to one, but instead of modeling the deep tissue movement of the cells using other cells as substrate, is going to use the a point this a substrate to pull itself forward. So it can be a single cell movement. So so more like what you have here on this top schematic. So let's just remind ourselves how links work in CompuCell3D. The regular links that have been used so far is between a cell and another cell, right? So that's going to be the distance between those two cells. In this new version, when you attach a cell center to a point space, we call it anchor. And the way it works is basically the same thing. So it's the same thing as before, but now the cell is connected to a point space, which is not another cell. So you can only move the cell forward or backwards, but you cannot move the other point. The other point is fixed, so that's why it's called an anchor. Okay. But the logic is exactly the same, of course, because you do not know what the anchor will be. This is something that you can only do at the Python level. You cannot do at the XML level, but you still have a lambda, you have a target distance, but instead of having another cell, you have a point in the space that you specify. Okay, so to use this, you still have to call the focal point plasticity in your wizard, okay? And then you have to add to create an anchor. That's the command that you use. You use anchor equals self new FP and then anchor. And then they first specify the cell, the strength of the force, the target distance, the maximum distance, and now you specify the position in space, the X, the Y, and the Z coordinates of the point space which you want to link your cell towards to, okay? And then that's what you will do. So our exercise for this one is start to create a model for the cell crawling, but now you only have a single cell and you make the links in front of cell every now and then, okay? And the cell keeps moving forward by links, by throwing new anchors at a given in front of it at a given angle allowance. Okay. So to do this, let's create a cell migration model with anchors. We'll do the same thing as before. Okay. Go to 3D++, create a new project menu, CompuCell3D project, then CompuCell3D project, call it cell model sequence 4, cell crawling anchors, Python XML option, hit continue. Let's use the same dimensions as before, 84 and 35. Make both directions periodic, hit continue. But now we only add one cell type, the cell crawler, Okay, you don't need to add the red cells. Okay, so you can just hit add incorporate the cell and hit continue, right? Again, ignore the chemical fill window, hit continue, and then select contact, volume flex, focal point plasticity, neighbor tracker, and hit continue again. And then the configuration is done. Okay. Okay. And if you don't want to go over this, you can just download the 6.2.4, and then you already have the model ready for you to see. Okay. So here's the simulation. You have just a periodic on the X is well, okay. This version is 300 and 100. Have a set crawler, okay, size 50, digital energies, the focal point plasticity. And notice that here I only have the local one. I don't need to specify cell type interaction because I'm going to create my links to the point space, going to be an anchor, so I don't really need to have the rest. And then in the form initializer, you see that I have X50, Y50, and X to 57, 57 with 7, so that just creates a single crawler cell on the left of my simulation. Right, so yeah, so just create a single cell and put the single cell on the left of simulation. And in the focal point plasticity, we just untag the local tag, so we can manipulate on the Python level. So let's now go to the steppable files. Okay, so in steppable files, I still have my math import and the random import. So now I also have the a random library that I import into the code. And I have all these globals, okay, the lambda, target distance, maximum distance. And I have a new ones here. I have the angle. That's just the angle at which we move with respect to x and y. X is going to move to the right. And I have I can ignore this n here. I have a range and a dA. Okay, the range is going to be the distance I'm going to create my anchor. And this delta A is going to be the delta angle at which I create in front of it. So it's going to be, I'm going to throw our anchor in front of it that's this of 7 pixels, but it can be anywhere within this angle range set by plus or minus 30 degrees. Now, okay, question from Anastasia. So I guess you don't need to initialize focal point parameters if you're using local. You can still initialize them. I think that's actually good practice. But you should usually use the max number of junctions to be 0, so you have complete control over the Python level. But in this case, you're not linking cell to another cell, right? So all those parameters that you have there is between different cell types, okay? Because in this example, you're going to use anchors. None of those parameters applies because it's going to link directly to the other cell, a cell to the point in space. So you still need the focal point plasticity plugin log on. You need the local tag to be activated, but you don't need anything else. Okay, so let's look at here the code. In this case, I didn't do any I didn't create any functions. So let's read this. So there's nothing happening on the start and the step. I have a waiting time of 1,000 Monte Carlo steps, and every 100 Monte Carlo steps, I go over all my cells. So in this case, just one cell. And what I do first I remove all the FPP links that cell has. So notice that this removes the links between cells and other cells, and also remove the links with anchors. Okay. Then what I do? Then I have these two variables here, okay, A and R. A is going to be I use the function uniform. That's a function that belongs to the random library, okay, that returns a random variable, okay, between those two values, okay? And these two values are going to be the whatever angle of direction that I have, minus plus some angle to minus another angle. So that's going to give me a range of angles between this and this value. Okay, this value here and this other value here. Okay, so if I have my angle set to 0, that's going to be give me the range between plus the A and minus the A on the x-axis. So is that here? So my angle is set to be 0, so it's going to be on the x direction. And this comment here returns an angle between this and this. Okay. So if my dA is smaller, it's going to be a small angle range. If my dA is bigger, it's going to be a bigger angle range. So in this case, I'm going to use 30 degrees. It's going to be plus 30 degrees here to minus 30 degrees here. Does it make sense? And this angle here can shift everything to be like that. Okay, so if I make that angle here to be 45 degrees, then the base is going to be here, and but the spread is going to still be the same. I'm not sure that's making sense to everyone. Nobody answer. But anyway, you are picking up a angle first, okay? And then this R here is also, I'm gonna select, I have a range between 2 and this range parameter is gonna be 7 pixels. So it's becoming what's gonna be the length of my anchor, right? That can be anything between 2 pixels up to 7 pixels. Okay, so that's going to be the length. So I could set this to be between, I could just have set this to be equal to the range, right? Like this, and then my anchors will always be 7 pixels wide in front of it with a different angle, okay? But if I do like this, it's going to be a length that's variable between either 2 pixels in front of the cell or up to 7 pixels in front of the cell. I hope that also makes sense. And once I define those two, I can use that to define where my anchor exactly will be. So it's going to be from the center of mass of the cell plus r times cosine radians of this angle, r, which is going to be this range, times sine radians of this angle. So I'm going to draw exactly where this angle will be. So if this angle was 10 degrees at a range of 5, then I'll be grabbing my cell, going to be, so if this was my cell, okay, this anchor will be at, let's say, 5 pixels, okay, because that's going to be the value of my R. So let's say the R is 5 pixels. There's a random value selected. And let's see that the random value selected for our angles to be 10 degrees. So going to be 5 up to 10 degrees, okay? So that will give me a position right here. So we're going to create my anchor. It's going to be here. So this is going to be the link my cell center from mass to this specific point in space. And I get this point by make this projection. So, question from Osman. Does it not mean that the anchor can be inside the cell then? Yes, it can be inside the cell. Can be in front of the cell, but that's no matter because what's pulling is not the cell, it's going to be the center of mass of the cell, right? So even if it's inside the cell, you're going to still make the cell move forward a little bit, okay? So remember, the anchor may be something that is within the cell, okay, or can be outside. So if that's you don't think that is reasonable, we can maybe make the range a little bit bigger, make it to be 10, right, and make this to be Yeah. 3.5 is going to be the radius of your cell because your cell is about 7 pixels in diameter. So that's going to be always in front of the cell in this case. But it's going to move the same way. Does it make sense? It still works, okay? So after you select exactly the point you're going to be, right? I use the command FP anchor cell. So I see which cell is going to anchoring, the strength, the target distance, the maximum distance. Remember, the target distance is 0. The maximum distance is going to be 1,000. So you're never going to break. And this is going to be X, Y, Z is going to be the points which I calculate based on the center of mass of the cell and how far it extends and what angle it deviates from the angle of direction. Okay. So after you do this, everything is all there already there, and you can just run the code and just get rid of this. And this is how the simulation looks like. I place my crawling cell here, and then after 1,000 Monte Carlo steps, the cell start to creating links and move itself forward. So if you want to just run the simulation, you can just download the code that shows here, okay? But basically that's the idea here. So if I make this, I can make this range a little bit wider. Let's make this 50 degrees, like I had before. And let's implement this range to be 10 and the minimum range to be 3.5. Okay, let me save, go back here and play the simulation again. Okay, and then you're gonna see that it's gonna still move forwards, but at a wider range, and the link is always in front of it. Okay. So there's another way to model cell crawling, but using anchors to move itself. Sorry. Question, is it also possible to do this by setting medium cell focal point parameters as I had before? No, you cannot do that because medium is not a cell object, so you cannot link it. It does not have a well-defined center of mass. So you cannot really do that with making a link between cell and the medium. Okay. Question, if the anchor is closer than the target distance, the anchor cannot never be closer than target distance. Wait, yes. If the anchor is closer than target distance, then you move backwards. Let's try to do this. Okay. Let's set the target distance to be 15. Okay, so it's always going to be close to the target distance and see, let's see what happens. Okay. So I just stopped simulation. I set the target distance to be 15, but the anchors are always made within the 5 and 7 range. So question for everyone, what do you think is going to happen? Would the cell still move forward? Would the cell move backwards? Would the cell move in another direction? Or would the simulation crash? There's one vote for stay, another vote for backwards. I guess Mark thinks it's backwards. Osman thinks it's going to be backwards. Okay. So people believe it's going to be backwards. Okay. So let's run simulation. See what's going to happen. If nothing happened right now. It's going to create a link. Okay, is that what you expected? I think this is very fun, actually. Thanks for suggesting this. I think so. The cell is moving forward, but it's in a very different type of mechanism, right? It's kind of, it's more like how we move. You set a point and then move away from that point, right? Um, I don't think, well, whatever, biology always do something weird, right? So maybe there's a cell that actually moves, propels itself forward by a mechanism that looks like this. Uh, yeah, it's being pushed instead of pulled. So it's pushing itself forward instead of pulling himself forward. Yeah, it's gonna get a foot. So yeah, you can also the code is there. You can use it to model whatever you want. Okay. One little setback of using anchors is that you can only specify one anchor per cell. You cannot specify more than one anchor, at least up to maybe that's different from version 4.7. I never tested, but you can only do one anchor per cell. But that's another way to do things. And you cannot only use anchors to make the cell move forward, you can also use anchors to actually anchor the cell. So maybe you can add external force to the cell, but the cell has an anchor at the exactly at the zero distance with its center of mass. That the force is going to push the cell forward, but the cell is anchored in the substrate, so the cell resists the force. So you can uh, deform the cell, but the cell kind of still anchored to where it is. Okay, so you can also use anchors to fix the cell space. The cell can still change its shape, can do the form, but the cell will not, you resist being moving center of mass. So there's another way you can use cell anchors. Okay. Someone pastes a code there, and I wanna, yes. So the the peers have already found the error, but that's something you can also do with anchors, right? You can also fix the cell space of instead of using it to make the cell propel itself forward. Okay. And you can do that for multiple cells. For example, you can, for example, let's make my X to, with a gap of, there. So this is going to be a simulation with about 7 or 8 cells. Yeah, 3 cells, okay. And each one is going to be creating its own leg and move itself forward. So yeah. Okay. So do you guys have any questions about these of anchors or this specific example? I didn't have time to talk about conversion extension, but basically these slides are there for you to check, okay? And basically to model the conversion extension, we're going to be basically use the cell crawling model as a base, but instead of extending links only to the right of the cell, we extend links to the right and the left of the cell, okay? And now the cell pulls from the both sides, okay? Use the links. And when the cell pulls from the both sides, is pushing out the cells to converge towards this line, and therefore your teeth start to extend on the other direction, okay? So the outer files that implement the different versions of convergent extension are there. Okay, the basis is again the cell crawling of deep tissues that you did as the first exercise here. And you can just grab them and see how the code looks like and play on your own pace at your computer at the end of the workshop, or maybe tonight before the next live tomorrow. So you see, the links is very powerful. You can do a lot of cool stuff with it. You can do a lot of uh, uh, maybe silly stuff with it. But that's why you need two models to cover all things. And there's even more things that you can do with links when you combine that to cell compartments, but that's going to be left for tomorrow. And Prion Adjapok is going to cover that to model tissue folding with links. Okay. So with that, I thank you for your attention. All the day uh, was me talking all the time, and I hope that was useful for you. And again, if you have questions, please let me know in the chat. And even after today, you can send me email, and I'll do my best to answer your questions by email after this.